Surface water reservoirs in varying sizes were built by our ancestors to store water for use during the dry periods. Especially for agriculture and for the needs of humans and the environment, small tank cascade systems organized as interconnected multiple tanks on the undulating landscape within a hydrological boundary found in the dry zone were a major part of Sri Lanka's glorious heritage, believed to have been invented over 2 millennia ago. These man-made tanks are designed in a way to get the maximum benefits of the northeast monsoonal rains. Tank cascades are considered to be one of the most efficient water management systems in the world, with water being recycled at each tank in the cascade system. A tank in a cascading system is not a distinct individual unit or something that works independently, but rather it is connected to many other tanks and components without which it cannot function properly. Bound together in a certain hydraulic pattern, the entire set of tanks functions as a single unit. A tank cascading system is a truly astonishing mechanism that works in harmony with the environment. A tank cascade system has 4 main functions. Firstly, it functions to capture water during the rains, minimizing floods. Secondly, they store rainwater on the surface and below the ground, enhancing the water security. Thirdly, tanks in the cascade allow use and reuse of water. And fourthly, they help in mitigating the drought effect in the dry zone, where water shortage is acute. The formation of a cascade system requires a landscape where water drains naturally in a branched or dendritic pattern. Tank cascades are formed by building tanks crossing the natural streams. A tank cascade, along with its components, is carefully designed and exceptionally well constructed for efficient water management covering all the seasons.
What are the boundaries of cascade? It's a good question, no doubt. To put it simply, one end will be the summit or a highland from which a water stream begins. It will be a very small trickle one. That is one end of it. Then on either side of that water path which is developing from the summit, you will have small ranges of hills. Sometimes they are mounds only, they are not hills, mounds, and they are not sometimes very continuous. Sometimes they are dissected, right? So those are the other 2 boundaries. Last boundary will be a point at which you cannot build any tank, any large tank, because the load of water that is coming from the side.
Each tank within a given cascade system has organized geographical and functional features which harmonize with the environment and are essential for water conservation and management. These functional components of the tank serve a specific purpose. The roles of these components can be explained very well with modern science, even though they were designed some centuries ago. A tank cascade system has a number of components, each of which serves a specific purpose to ensure that good quality water is supplied throughout the year in adequate quantities. There are differences in the number of components present in tanks in a cascade system depending on the landscape position and the utility of the tank. In a system, the first set of components have been designed to improve the quality of water entering into the tank from the catchment by a series of filtering systems. Kuluwaba, also known as the forest tank, waterholes known as Godawala and Harakwala, all located in the catchment of the tank, retain dead leaves, other debris and mud or sediments. Next, before the tank, is a grass cover known as the Perahana, meaning filter in Sinhala, which is located between the catchment and the high flood level for purifying the water by holding granules of earth and sediments. This is very similar to the preliminary treatment step in modern wastewater treatment systems. The now clean water then enters the tank for human consumption and agriculture. The water stored in the tank is protected from evaporation by tree belts, naturally growing along either side of the uppermost area of each tank. These are called gas gommana. They act as windshields and minimize the dry wind contact with the water surface, thus minimizing evaporation. The Kattakadua, or interceptor, is a thick strip of vegetation located between the tank bund and the paddy fields. It also functionally consists of a water hole named Yaturuwala to retain the saline water seeping from the tank. Various plants with a salt-absorbing ability are found in the Kattakadua, which helps to reduce the salinity of the water seeping from the bund before it reaches the paddy field. In addition, the Yaturuwala minimizes seepage losses from the tank by raising the downstream water table. Irrigation water used for cultivation is to be disposed through a drainage canal. A common drainage known as Kil-Ella is used for this purpose. This ensures the prevention of salt accumulation in the paddy field. A salt-affected soil does not produce a good yield. In addition to their main functions, the gas gommana, or the tree belt, and the Kattakadua also contribute to the stability of the tank ecosystem. They also function as nature reserves, where a rich assemblage of biodiversity is formed, which in turn provides multiple benefits to the community. According to folklore, tank cascade systems have been in continuous existence and use from 400 BC. By 1200 AD, it is assumed that almost 15,000 small tanks were either fully or partly operational. Although there was a decline and decay of the major irrigation systems of the dry zone from 1200 AD onwards, these small tank systems continued in varying degrees of operation. Following independence in 1948, the responsibility for maintaining minor irrigation schemes was taken over by the Ministry of Agriculture, and with the introduction of the Paddy Lands Act of 1958, the Department of Agrarian Services was entrusted with the responsibility of maintaining all village irrigation schemes. With this change, the participation of the communities in tank maintenance decreased, and the community became dependent on the government for tank operation and maintenance. During the past 50 years, very little or no attention has been paid to tank systems as a whole, but only on individual tanks. By now, farmers had to face unforeseen problems owing to the construction and restoration of single tanks in isolation, ignoring the interconnective nature and functionalities of cascade systems.
Every village here had a patch of forest called Gankala, and then that is disappeared now. Why? Our land use pattern has changed. Say in the 1970s, there was a big rush for things like chilies and onions. So the chili cultivation spread and all the forests were cut down, right? Not all, there are some remaining. And then in the 1990s, the sweet corn cultivation, Badairingu, became the main earner for these areas. Even today it is so. So for Badairingu or sweet corn, all the remaining forest patches were cleared, irrespective of whether they are in the tank catchments or not. So therefore, there is more siltation now in the tank because there is more erosion. And on top of that, the population has increased and people have encroached even on tank reservations, right? It is very difficult to take them out of it.
Tank sedimentation due to soil erosion is the main factor leading to the deterioration of tank cascade systems. Upland farming practices, including shifting cultivation or chaina without appropriate soil conservation measures, is one of the causes. The runoff water from the upper catchment of tanks brings loosened soil as sediments without appropriate soil conservation measures and results in tank siltation. Sedimented tanks hold less water with reduced key tank functions such as flood control, groundwater recharge, water supply, and drought mitigation. Over the years, the tanks dry up completely and the paddy fields become abandoned land. In terms of water quality, in addition to the silt, heavy metals and chemical residues from pesticides and fertilizers that are applied to paddy fields in the upper areas of the cascade system have the potential to pollute tank water. There is also a poor understanding of tank components at present. For example, forest tanks, which are supposed to function as filters, have been wrongly used for irrigation. Finally, the environment surrounding almost every tank has deteriorated tragically. Water pollution has resulted in the depletion of aquatic plants and animals. Moreover, the environment is deprived of birds and insects owing to the destruction of vegetation. Trees growing naturally in the tree belts in the upland areas of the tank are felled indiscriminately.
Ecological restoration of cascades has been one of our interested areas, and we were looking for a donor to finance that type of a work. Then we got to know that the HSBC, under their Global Water Programme, they are supporting projects of that sort. So that was a interesting finding, and we submitted our proposal, and they have provided resources for us to implement this project for 3 years.
Through corporate sustainability at HSBC, the bank aims to contribute to the social and economic development of the communities, safeguard the environment, and also develop and support culture and heritage in Sri Lanka. The project will vastly benefit over 60,000 people with access to safe drinking water for everyday living and livelihood development. The project carried out scientific restoration of the Kapiriggama tank system and developed a sustainable management mechanism with the full participation of local communities and regulatory bodies.
One of the aspects that made the IUCN-HSBC partnership project unique was that it was a fully consultative process. This means that all stakeholders, or everyone who could affect or be affected by the project, was consulted to obtain their views and advice. Among those consulted was the Department of Agrarian Development and members of the local community. In addition, a national consultative committee consisting of national tank cascade system experts and representatives from key agencies was formed. Other than the broader objective of developing a model for the ecological restoration of a tank cascade system in Kapiriggama, IUCN had no predetermined specific activities of the project before consulting the stakeholders. The activities were only decided after consulting the community and therefore were based entirely on the needs of the community and the technical feasibility. The project aimed to solve key issues associated with the cascades such as low cropping intensity, tank sedimentation, high tank water loss, and low productivity of land. An integrated, multi-stakeholder approach was used to solve these critical issues. The project used a balanced approach where the physical restoration of tanks, ecological restoration of tank catchments and their surroundings, improvement of soil and water quality, enhancement of soil productivity, efficient management of water, community empowerment, livelihood development, strengthening of institutional mechanisms, and knowledge dissemination have all been addressed.
Our approach to this project was, we first had a field visit where we wanted to study the existing situation with respect to environment, socioeconomics, and agriculture, all that. So we studied the present status, then started realizing the issues the system is having.
IUCN adopted a science-based approach. The Department of Agrarian Development was identified as the key implementing partner. Initial activities included stakeholder engagement and information generation, such as village-level consultation meetings and socio-economic surveys, which provided an understanding of the existing situation of the community and identified their needs. The officers from the Divisional Secretariat of Rambawa, students of the Rajarata University of Sri Lanka and staff of HSBC took part in these. Biodiversity surveys and ethnobiodiversity surveys, which is the study of interactions between humans and biodiversity, were carried out by IUCN staff. The Department of Agrarian Development carried out investigations on tank-related physical infrastructure conditions, tank bed geometry, and depth of sediment in the tanks. In the end, restoration needs were identified for 18 tanks in the Kapiriggama Cascade system. The progress of the project was continuously discussed with the donor, HSBC, the community, the Department of Agrarian Development, the Divisional Secretariat of Rambawa, and other stakeholder parties. One such platform on which this was done was the Divisional Agriculture Committee of Rambawa. At the end of initial studies, the restoration of the tank cascade system began by prioritizing activities based on scientific reasoning coupled with community needs. For implementation, 8 farmer organizations in the area were empowered to carry out tank infrastructure work and partial desiltation work. IUCN and the Department for Agrarian Development provided technical assistance. Shramadana, or donation of labor, is a traditional way the community provides free labor for the greater good of the community. In this context, HSBC volunteers also helped in Shramadana campaigns for restoration work and in surveys. Therefore, the HSBC Bank not only provided the funding for the project, but also actively participated in the implementation of the project. Once labor was mobilized, the main restoration activities started. Rehabilitation of tank-related infrastructure such as banks, sluices, spills, distribution canals, culverts, and service roads of 18 tanks was successfully completed. The concept of partial desiltation was used in desilting the tanks. This concept focuses on changing the tank bed geometry to minimize water loss while removing silt from the tank bed. Thus, partial desiltation not only improves the storage capacity of the tank, but also conserves water. The methodology to remove silt or partial desiltation is provided by the Department of Agrarian Development.
The siltation of a tank is not a bad thing. It is always useful for the tank. It means that it controls the seepage and percolation, reduces the rate of seepage and percolation, and increase the overall efficiency of the tank system. But the problem is the over siltation. This tank got silted more than 1 meter and affected its capacity. Finally, we decided to undertake a soil survey in the tank bed that was introduced by the Water Management Division of the Department of Agrarian Development. So we divided the tank bed by surveying methods into 25 and into 25 meter grids and grid intersections, and undertake borehole surveys at each and every grid intersections, and finally found out the depth of siltation and the places where the tank got silted. We were able to execute in this particular study under the IUCN project, and I think that was succeeded.
Over 38,000 cubic meters of silt was removed from 5 tanks of the cascade. The removed silt was then deposited as mounds at the upstream of the tank, or in the catchment in the form of ridges to trap silt. These mounds, planted with trees, would provide habitats for birds and other wildlife.
We have removed certain part of the soil, heaped up in the upstream or carted away from the tank. So that really brings us not only the expansion of the capacity, but also now the water can be kept for a long time. That means farmers can cultivate Yala season, Maha season, and the cropping intensity of that has increased drastically.
A number of soil conservation methods were introduced in the tank cascade to prevent soil erosion and tank siltation. Soil conservation in turn would improve farming and ecosystem productivity. This included the establishment of soil conservation bunds in the upland of the tanks to prevent erosion. Upland farmers were also educated and trained so that they could build soil conservation ridges and refrain from carrying out deep soil tillage. The project established 37 soil conservation demonstration sites covering an extent of 33 acres. Overall, more than 20,000 meters of soil conservation bunds were established over 100 acres of land in the immediate upstream of the tanks. This will reduce soil erosion and the sedimentation of tanks significantly. To increase soil health and fertility, organic and traditional rice farming were promoted among 250 farmer families in the area. Organic farming uses lower amounts of agrochemical pesticides and fertilizers, minimizing the potential soil and water pollution. Use of organic matter as soil amendments such as compost and crop residues improves soil texture, health, and fertility. Use of biopesticides and fertilizers made from natural, non-harmful substances were also introduced. The use of traditional rice varieties also reduced the need for agrochemicals. To restore the tank ecosystem, a large-scale replanting program involving the community and other stakeholders was carried out. More than 7,500 plants were planted in the Gasgommana and Kattakadua areas in 13 tanks. Suitable native plants were identified by IUCN Flora experts and used for replanting. Awareness raising amongst members of the community was carried out throughout the project and also included trainings on tank cascade systems and their management, organic agriculture, traditional rice farming, soil conservation, irrigated agriculture, and health awareness on chronic kidney disease. About 1,200 community members, 350 school children, and 100 officers were trained in these programs. In addition to this, a series of awareness materials were developed and made freely available to reach a wider audience. Such materials included training manuals, technical notes, information sheets, and documentaries. Proper irrigation and water management requires data such as tank water availability, rainfall amounts, other basic meteorological data, and water flow data. The project established an agro-meteorological station and other gauging equipment in the project area to facilitate increased data use in decision making. For this purpose, the project trained farmers and officials in collecting and using data for water management. The institutional framework of cascade management was also strengthened at different levels. Through their involvement in project activities, the farmer organizations were now empowered to restore, rehabilitate, and maintain their own tanks. In addition, a cascade management committee was established for the management and maintenance of the tank cascade system and its natural environment. These would ensure that the community could maintain their tank cascade system long after the project had ended. The Department of Agrarian Development also adopted a number of improved mechanisms such as partial desiltation and soil health monitoring as significant improvements to its governance. At the end of the project, it was clear that a number of immense achievements had been made. The project had demonstrated a replicable model for the scientific and ecological restoration of a small tank cascade for enhanced socio-economic and ecological benefits. a successful multi-stakeholder approach to restoration, engaging government agencies, technical experts, communities, NGOs, and the private sector had been employed successfully. Tank-dependent communities had become empowered by engaging them in the planning and implementation of the entire program. Ownership had been built amongst key players including government institutions, as well as the local community, through IUCN's catalytic role in designing and implementing the project. The open and transparent approach of information flow added value to the process by bringing in all stakeholders into the project while ensuring maximum inputs and ownership. All project lessons were now freely available as knowledge products for the betterment of future interventions involving tank cascade systems. The project has already contributed and has been proposed to be used as a model for the development of a large cascade restoration project to be funded by the Green Climate Fund, covering about 30 cascades. The North Central Province Canal, a mega irrigation development project funded by ADB, also expects to use cascade systems in its design. And finally, the project has influenced the Department of Agrarian Development to consider a policy change in using the collective cascade approach for small tank restoration initiatives.
The whole restoration is considered as an integrated management practice that can be replicated in other cascades in Sri Lanka, and also when the North Central Province Canal progress to take that additional water into cascades before giving to the paddy fields.
This project has substantiated the notion that in order to increase the productivity of farmlands associated with minor tanks in the Rajarata area, it is imperative to launch a program to restore tank cascade systems rather than rehabilitating individual tanks. For any future proposals the government or any other institution may have in this regard, the Kapiriggama Cascade Tank System Restoration Project, funded by HSBC and implemented by IUCN, would undoubtedly serve as a guiding example.
පුරා පැන් අරගෙන බීපල්ලා අපේ ගමේ නෙළුමට පිං දීපල්ලා